Yesterday class we were discussing about like a joint distribution. Like if we are having more than one random variable, then what we will do. So in that case, okay. So like if we are having more than one random variable, suppose now we are having only two random variable. One is capital X, another one is capital Y. And for this x and y, we are taking any sample point from the sample space, and this sample point s is mapped by the random variable capital X at this point and capital Y by this point. So this is actually the range of the random variable xy. So this is the range point of the random variable xy, and we sometimes represent it by like xy. So how we define the event here, like this, you can see this s belongs to s such that x of s less than equal to x and y of s is also less than equal to some y. So this is the way we map sample space through two random variable. We can map more than one random variable also. So today lecture the title is the expert characterization of nanomaterials. Okay. But my PPT presentation is based on the characterization of nanomaterial as well as the bulk materials. So if any questions or doubt, please write in the chat room. Then we will discuss later. Like if we are having two random variable x y, so the joint random variable is denoted by this x comma y, or we may represent the joint random variables like this x comma x y dash, that is it's a column vector x y, and we can extend to this any number of random variable. Like if I'm saying x1 is a random variable, x2 is a random variable, xn is a random variable, then it is a column matrix like having elements x1, x2, xn. Suppose we are interested in studying the height and weight of the student in a class, so we can define the joint random variable xy, where x represents the height and y represents the weight. And suppose in a communication system, x is the transmitted signal and y is the corresponding noisy received signal, and this can be a joint random variable. Nanocomposites, that is three-dimensional materials. So today we also discussed in yesterday class this the event x less than equal to x. If for the case of one random variable, if we are having two random variable like x and y, then this is the event x less than equal to x, y less than equal to y. And what we mean by this, x less than equal to x intersection with y less than equal to y. And the probability of this event, the probability of this event is known as the joint distribution function, or you say that joint cumulative distribution function, and denoted by fx comma y, x comma y. So this is the case. So like here, this is the event we are saying x less than equal to x, comma y less than equal to y. So it is actually the containing those sample points such that sample point s from the sample space for which x of s is less than equal to x, and or you say comma, we can use comma y of s is less than equal to y. So those sample points belong to this event for which x of s is less than equal to x and y of s is less than equal to y. Then like if we are having two points
x1 and this y1 and y2 on the other real line, then if x1 is less than equal to x2 and y1 is less than equal to y2, then this event is actually subset of this event. Because x less than equal to means x, first we see this one, this x less than equal to x2 and y less than equal to y2. So we will see this event first. So this event is actually like if this is the line x equal to x2 and this is the line y equal to y2, and because this is a, we cannot plot infinitely, but it's like a whole yellow region, like x less than equal to x2 and y less than equal to y2. So this is this event, and the blue region is this one for this event, x less than equal to x1 and y less than equal to y1. So obviously this is the larger set and this is the smaller set. So all the sample points belongs to this domain are again belonging to this larger domain. So the probability of this larger set is greater than the probability of this set. And this probability is the cumulative distribution function at x2, y2 for the random variable x comma y, and this is for x1, y1. So then we have already discussed this. Like if one of them is say if minus infinity, like if x is minus infinity, then it's the intersection of this is this, and obviously this is an empty event, so we will have this one, and it is 0. So the because one this event is empty, so intersection of this is with any event actually empty and will give you 0. And also in here it actually notation is saying that this intersection this is a subset of this. Obviously you know that if you have two sets A intersection B, and you know that this intersection is always a subset of A and also B for also because it's the intersection. So this is the joint event, and this joint event is a subset of this event, and the probability of this event is 0 for the case of one random variable. So it is also, because if this is 0, then its probability is less than equal to this one, so this is also 0. Similarly, we can do for the y, if y is minus infinity. And for plus 1, same thing we can do like this also. If both are infinity, then it is 1. So we remember this result, actually this, we have to remember this is 0, this is infinity, infinity, which is 1. And then this is like fx is the right continuous in both the variables. Then this result like x1 is less than equal to x2 and y1 is less than y2. Then this probability, because we have already proved this result for the case of one random variable. Now for the case of two random variable, it is like this: xy, x2, y2, xy, x1, y2, xy, x2, y1 plus f of xy, x1, y. These results also we. Then we have talked about the marginal distribution function, that from the joint distribution function we can calculate their marginal distribution functions. So here like if this is joint, because here x and y are two random variables, so if we replace y by plus infinity, so what does it mean? That x less than equal to x intersection with this event, and this is event is actually uh, sample space. So sample space intersection with this event is with this event only. So the probability of this event is actually equal to this one, and the probability of this event is fxx, and probability of this event is this one. So if you put second variable in the joint this joint distribution function, if you substitute, if you put y equal to infinity, or you take limit y tends to plus infinity, and the joint distribution of x and y, you will get the distribution of x. Similarly, you can take limit x is also tending to plus infinity, then you will get the marginal distribution function for y. Okay. So you have to remember these two results also. So like we will solve one problem on that. But this is the joint distribution function. It is already defined or given to you for the case of two random variable capital X and Y. So for x greater than equal to 0, less than plus infinity, and here it is comma means and y is greater than equal to 0 and less than equal to plus infinity, it is having this definition. Okay. Otherwise, like when y is less than 0 or x is less than 0, if any one of them is less than 0, the value of distribution function f of x comma y small x comma small y is actually 0. So now from this, in this problem, we have to calculate marginal distribution function. So marginal distribution function means we have to calculate this distribution function for x. So distribution function of x, if I want to calculate, then I have to make this y plus infinity. So I have taken the limit y goes to plus infinity. In the definition of joint distribution function of x and y. And you can see in the previous slide like this. This is the joint distribution function of x and y. If I make y equal to or y is going towards plus infinity, then e raised to power minus infinity is 0 and then it becomes 1. So 1 into e raised to power minus 2x. So you are getting this one. Similarly, when you take this x is tending to infinity, then this part will goes to 1 because it is a raised to power minus 2 into infinity, and this is actually 1, so you will get this one. So this is the way you calculate marginal density function from joint density function. Now if we want to calculate this probability that x is greater than 1 less than equal to 2 and y is greater than 1 less than equal to 2. So to calculate this probability, we use the result to that probability that x1 less than x less than equal to x2, y1 less than capital Y less than equal to y2 is equals to joint distribution fxy x2 y2, then minus x1 y2 and y2 x1, and then plus x1 y1. So if we use this result, and we have already known fxy, so from there we can write like this. So we have this result, this one, to calculate the probability, and here we have the definition here. So if I substitute here x equal to 2 and y equal to 2, I will get f x to 2. So f x to 2 is 1 minus e raised to power minus 4 into 1 minus e raised to power 2. Similarly, if I put x equal to 1 and y equal to 1, I will get this, and like this I will get, and after simplification I will get this as the probability. Then jointly distributed discrete random variable, like if you are having two random variable x and y, then joint probability mass function is defined by this pxy x comma y, and it contains those sample points for which x of x is equal to x and y of x equal to y. For all xy points belongs to the range of x and range of y. So this is called the joint probability mass function for the case of two discrete random variable. And this we have already discussed this one also, that total probability is one. Like if we sum over all values of x and y, this joint probability mass function, then we will get one. So this is also one property. Here they have provided the proof for that. Now this actually useful. How to calculate, earlier we are able to calculate marginal distribution function from joint distribution function. Similarly, we can calculate marginal probability mass function from joint distribution function. So you see this one. That probability x. So we know that if it is x is a discrete random variable, it is that probability at x equals to x. And here we have taken union with ry, that is a whole range set of y, and then it means it will give us probability that x y x y. So if I add all the proper joint probabilities for the range of y, that is, if I add a joint probability mass function for all values of y belonging to the range set of y, I will get the probability marginal probability mass function for the x. Similarly, if I add joint probability mass function for all values of x, I will get marginal probability mass function for y. Then here is one example. So this in this earlier we are writing this probability mass function like for x equals to 0, we write something we are getting, and for probability that x equal to 1, we are writing something whatever we are getting. Since here we are having two random variables x and y of discrete kind, so we have written them like this. And here x is taking values 0, 1 and 2. These are the values taken by the random variable x. And y 0 and 1. So these are the two values taken by the random variable y. So now, because here we have to calculate the probability like what is x equal to 0, comma this what is y x equal to 0. This probability we want. So to depict this probability, we have written in the form of table that when x equal taking the 0 value and y is also taking that 0 value, then this probability is 0.025. So similarly, the probability of x taking one value and y is taking also one. So from this table we can say that this is the intersection point for x and y. So this probability is 0.35. Similarly, probability of x equals to 2. Yes. X equals to 2, comma, y equals to 0. So you see this intersection point, this is the intersection point. So what is the value? 0.1. So we have given here the joint probability mass function for the random variable x and y. And it is actually this one. These two values are giving us the joint probability mass function for the random variable x. Now, if I want to calculate marginal probability mass function pxx or pyy, so if you remember the formula, pxx is equals to the summation over y. Actually, we have to run on all values of y belonging to ry, and we have to add this probability that x equal to x, comma y equal to y. So this is the formula for calculating this marginal probability mass function for x from the joint probability mass function of x and y. So here I can see that if I have to calculate this, so here I replace this x by 0 because first point of x is 0. So if x is 0, so this x is also replaced by 0 here, and now the index run over this. So that means I have to add all the probabilities, and y is taking how many values? Ry is having these two values. Here in this particular example, Ry is having only 0 and 1. These are the two values taken by. So one time I is y is 0 and second time it is 1. So it means I have to add this value for y equal to 0 plus so if I this one. The solution is so if this summation we expand, so one is this one and another probability that x equal to 0 because x is not changing and y is taking another value this. So the sum of these two probabilities will give me the probability for the marginal probability mass function for x at 0. So I add these two probabilities. So this probability is so the first this probability that x equal to 0, y equal to 0 is this one, and probability that x equal to 0 and y equal to 1 is this one. So I have to add these two, and the sum of these two is actually this one. So if our random variable is of discrete kind, then what we do, like this is the value for x equal to 0, I will add the all the probability for this column and I will get the probability, marginal probability at x equal to 0. Similarly for x equal to 1, I add these two and I will get this one. So this is actually, this 0.45 is actually probability at 1, this 0.45, because I have added this. Similarly for 2 also, like if I want to know this 2 for 2, so I have to here what I have to do here is I have to write 2 here. This is also replaced by 2, and then I have to add these two, and these two are one is this one, second one is this one, and the adding will get this one. So finally, if we are adding columns, we are getting probability, marginal probability mass function for x. So this is the value given here for the probability, marginal probability mass function pxx. Similarly for y also you can do. So for y it is like this, probability that for y is equals to summation over all x belonging to rx, and probability that x equals to small x and y equal to small y. But here, since we are calculating for y, so this y actually replaced by the value. So like for 0, if I want to calculate, so 0. So here this is also replaced by, this y is replaced by 0. And now I have to run this summation over the rx, and rx is having taking three values. Here rx is 0, 1, 2. So first it is 1. So 1, 0, 1, 0 is this point. Sorry, rx take first 0. So 0, 0 is this point. Then r take x take 1. So 1, 0, and then 2, 0. So if I add these three probability, and then I will get the probability of y at 0. So the sum of these three probability is given here. So it is 0.5. Similarly, if I want to know for 1, I will write here 1. Here again I will write 1. And then I will run this index of summation over rx, and rx taking three values 0, 1, 2. So for 0, 1. So if x is 0 and y is 1, this one. If x is 1 and y is also 1, this one. If x is 2 and y is 1, which is this one. Sum of these three will give you this one. So this is the way I calculated the probability mass function for the random variable, marginal probability mass function for the random variable y. It is the sum of the values in the rows of for the like points on the real line. This is 0 and 1 are the point on the real line for y values, and if we add the probability of these rows, we will get the probability mass, marginal probability mass function for y, similarly for 1 also. So this is the way we calculate. Now we go to the case of continuous random variable, and now like earlier we have probability density function, here we have joint probability density function. So if x and y are two continuous random variables with their joint density function, both are continuous, then the joint density function is defined by this f of xy del 2 over del x del y f xy like this. And if you have joint probability density function of a continuous type random variable, then you can get its joint distribution function fxy by using this result. So you have to remember these two results also. Minus infinity to x, minus infinity to y, fxy, uv d u. Now, we have learned this joint probability mass function, and we are calculating a marginal probability mass function from the joint probability mass function. Similarly, we can calculate also marginal probability mass function from the joint probability density function. So first we see the property of joint probability density function. It means this is always greater than equal to 0 for all values of xy belongs to R2, and if we integrate over the whole R square domain, that is minus infinity to x, this x is taking values minus infinity to plus infinity, y is also taking minus infinity to plus infinity, and you are integrating this joint density function over the R square, then you will get 1. So these properties are also useful. Then we can calculate the marginal density function from this joint probability density function. You will see the formula here. So this is the formula. Like if I am having joint probability density function and I integrate this with respect to one variable y, 1 minus infinity, then I will get marginal density function for the random variable x. Or otherwise, if I integrating this joint probability density function with respect to the variable x within the whole domain minus infinity to plus infinity, I will get marginal density function of y. So this is the way we can calculate marginal density function from the joint density functions. So in this problem, we have to calculate the joint density function fxy from the joint distribution function. If you remember, example 3 is this one. This one is there. So here in example 3, only this joint distribution is given to you, and you have to calculate joint density function. And you know how you can calculate joint density function from joint distribution function by using this f of xy del 2 over del x del y f of capital F of xy. So we will see. So we have to differentiate this capital F of x comma y. to get the joint density function, and the value of this is this one for all values of x greater than equal to 0 and y greater than equal to 0. And since it's a partial differentiation, and you know that the differentiation of this with respect to x give you only 2 e raised to power minus 2 e raised to power minus 2x, and similarly for this you will get minus y raised to power minus I, and then minus minus will be plus, and you will get this one. So this is the joint density function you have obtained from the joint distribution function. Now, like in this example 6, the joint PDF of two random variables x and y is given by here. So here the joint density function of the two random variable x and y is provided fxy x comma y equals to cxy x greater than equal to 0 less than equal to 2 and y greater than equal to 0 and less than 2, and otherwise it is 0. So if x is less than 0 or greater than 2, it is 0, or if y is less than 0 or greater than 2, it is 0. So this is the your joint probability density functions for x and y random variable, and here you have to calculate c first, and then you have to calculate the joint distribution function from this joint density function, and then you have to calculate a marginal density function for x and y from this joint density function, and then you have to calculate this probability also. So see, so we see that this is our joint density function. It is cxy when x is greater than and less than equal to 2, and when y is greater than 0 and less than equal to Nagaraju, mute your mic. Nagaraju. Hello, Mr. Nagaraju. So now we try to calculate C. So we know that the one property of joint density function is this one. This total integration should be 1. So we'll use this definite property and try to get this C. So we'll get this C. That means we are integrating this whole from minus infinity to plus infinity fxy xy dx dy, and we know that for other domain it is 0, and with this domain it is having value cxy when x is greater than 0 and less than 2, and y is greater than equal to 0 and less than 2, and for other domain it is 0. So we will have this one. So here x and y can be split like this, and then we integrate, we will get 4c, and this 4c is actually this thing we are assuming that is this actually equal to 1. So the value of this is 4c. So 4c is equal to 1, and you will get c equal to 1 by 4. Now from this, so we have obtained the value of c, and we substitute this value of c in the here. So this value of c will be substituted here, and then we try to calculate this joint distribution function from the joint density function. So this also we I told you this that how we calculate this. This is the formula to obtain joint distribution function from joint density function. So we'll use this formula minus infinity to x minus infinity to y f x y u v du dv. We'll use this one. So like this is we have used already. So here we are assuming that our domain is x greater than equal to 0 and less than equal to 2, and y is greater than 0 and less than equal to 2. For other domain, our f x this f of x y is 0, so it is 0. So for this domain we have something which is non-zero. So in this domain, this f of xy is having definition c into xy. Since we are using the variable uv, like minus infinity to x and minus infinity to y and x, y, u, u. So since f x y u x for x y it is having value c x y, so for u v it is having u and v, and c is already calculated 1 by 4 and integrated with respect to du and du. So the integration of u with respect to du will give you u square by 2, and when you substitute the limit, like so here u goes to minus infinity and this is v goes to minus infinity to 1. So when you substitute u square by 2 and you have to substitute minus infinity to, because it is 0 to x, so you will get x square by 2. Similarly, you will get y square by 2 and 1 by 4 is outside and you are having this one. Then once you have this joint probability distribution function from giant density function, now you have to calculate this marginal. So the marginal definition is that you have to integrate for one variable, like from y equal to minus infinity to plus infinity f x y x y y. So here, since we know that the joint density function is having cxy when y is greater than equal to 0 and less than equal to 2. So this domain minus infinity to plus infinity is restricted to only this, because in this domain value of y it is having something, otherwise it is 0. So for y equal to 0 to 2, cxy and cxyl, c is 1 by 4, so we have written this, and we are integrating with respect to y, so it is y square by 2, and so y square by 2, and you have to substitute the value of y 0 and 2. So for 2 you will get 4 by 2, and 4 by 2 means 2 in the numerator, and there is 4 also available in the denominator, so finally you are having x by 2. So this is the marginal density function we have calculated from the joint distribution function. Similarly, you can calculate for y also. In that case, you have to integrate with respect to x. If you integrate this minus infinity to plus infinity with respect to x, you will get this. So this is the way we calculate marginal density function from joint density function, marginal distribution function from joint density function. Now the last part is to find this probability. So to calculate this probability, we know that if x is greater than x1 less than x2, y is greater than x1, y1 and y is less than equal to y2. So this probability can be rewritten as in terms of the joint distribution function like this: f x y 1 1, because this y2 and x2 are here 1 1, then 0 0, and then this. And you use the definition of distribution function, which is already given in the there. This is the definition we have calculated. So for 0, it is 0. Like if any one of x and y is 0, it is 0. So for x equal to 1 and y equal to 1, you are having 1 by 16. So here, because if any x or y is 0, that value is 0. So these three terms are 0. So for only this term, you have 1 by 16. So this is the probability of this event. Then conditional distribution. So conditional distributions are that random of okay. Now we discuss this already discussed. Okay, now we go to this notebook. So Now, if in exam I told you to solve this problem, a fair coin is tossed three times and x is a random variable defined by x is the number of heads and y is another random variable and y is taking the value, absolute value of the difference between the number of heads and tails. Find the joint probability mass function and joint probability distribution function for the random variable x, y. So like if this much question is provided to you, only this that much. So here probabilities are also not provided to you. Joint probability mass function you are not having, so you have to calculate that one. Just you have information that the coin is fair, it is tossed three times, and on the basis of this experiment, I decided x is the number of heads and y is the another random variable, and which taking values which is defined by the absolute value of difference between the number of hand and number of tails. So I know from our experience that if there are three, if a coin is tossed three times, then this is the sample space. This is the sample space. And TT. So this is the outcomes of the experiments. And on the these outcomes, we define the value of x. So like x taking this event to 3 because it is having 3 heads, so number of heads. So this event is going to 3. Now this event is having 2 heads, so this is going to this. This is also going to this. And this is also going to this. Now the remaining events like this one. This is good because it's having one head, this, and this. So these three events goes to this one because they are having one head. And then no head case is also there. So this is going to 0. This is the value taken by the random variable x to map the sample points. Now we come to the y. Y is the absolute difference between the number of heads and the number of tails. So here the number of head is 3 and number of tail is 0. So absolute difference is 3. So this is going here. Similarly, this is also going here because the number of tail is 3 and number of head is 0. So absolute value is 3. Now we go to this. Here two heads and one tail. So number of head minus number of tail is 1 and absolute is 1. Similarly, it's for this. So all these values are mapped to 1 as per the definition of y. These values because the absolute difference of number of heads and number of tail is 1. So these are the value taken by the random variable y. Now I define because notational convenience I used to write like x equals to xi so that it is easy to remember for the case of single random variable, and if it is two random variable I write like y equals to yj sometimes, and I denote this thing as p I j for the case of discrete random variable, not for the continuous pij. So pij is actually the way of writing the joint probability mass function for the two discrete random variable x and y. So if I write somewhere pij, I mean by this probability that x equals to xi and y equal to yj. And what are the xi? Xi's are the any value from this Rx and yj is any value from R. So now I define the map of this x, how they are actually. So for the case of Rx, xi is I, for I goes to 0, 1, 2, 3. So xi is having 0 value, 1 value, 2 value and 3 value. And for this yj, I am indexing y as a 1 and 3. So I'm not taking it starting from 0 to 2. So that it will become convenient to understand that for j equal to 1, yj is 1, and for j equal to 3, it is 3. So my index for j is like 1, 3. So here I am having this xi and yj, the values taken by the random variable capital X and Y. Now I calculate this what we call Pij. So Pij I have to calculate for each I ranging 0, 1, 2, 3 for each j from 1 and 2. For each j 1 and 2 and I 0, 1, 2, 3. So that means if I want to know what is P0, P0 means I is 0 and j is 1. So P01, it means x equals to 0 and y equals to 1. So I have to find the intersection of the event in which number of heads are 0 and the absolute difference remains the 1. So number of heads are 0, there is only one event in which number of heads is 0. But here the absolute difference is not equal to 1. So it means there is no such event where the number of head is 0 and absolute difference is 1. So it means it's a null event, it does not belong here, so its probability is 0. So I'm creating this table. For x equal to 0 and y equal to 1, the probability P01 is 0. Now I try to calculate what is P03. So P03 means probability that x equals to 0 and y equal to 3. It means no head, but absolute difference is 3. So I know that there is one event in which there is no head, but absolute difference is 3. And know that this is only one event out of 8 events. So its probability is 1 by 8. So I write the probability that this. So for x equal to 0 and y equal to 3, I am having this one. Similarly, to calculate P11, for which x equal to 1 and y equal to 1, it means number of head is 1 and absolute difference is also 1. So number of head is 1 and absolute difference is 1. These are the three events and each are equally likely. So its probability is 3 by 8. Similarly, P13, that number of head is 1, but still absolute difference remains 3. So there is no such event in which number of head is remain 1, but absolute difference is also 3. So it's a null event, so the probability is 0. Then number of heads 2 and absolute difference 1. So we are also having this like HHT, THH and HTH are the three events in which number of heads are 2 and absolute difference remain the 1. So the probability is 3 by 8. Now like the third is that P23 is the event in which the number of heads 2 and absolute difference is 3, but this is not available any event, so it is 0. So like this, I have created this joint. I have created this joint probability mass function for the random variable x, y as defined in the problem. So this is the joint probability mass function. Now, from this joint probability mass function, I have to calculate marginal probability mass function. So, one step ahead. Okay, we'll talk about this later, but we come to the question again. So, how to calculate this? Actually, for you, I already discussed this thing through PPT. The marginal probability mass function of x is defined by this. What I write, like I have to calculate probability that x equal to xi. This is the probability mass function for x, and I denote this in terms of two random variable like Pij. So it means j is varying for all, and I am calculating. So for probability that x equal to xi, like this is equal to probability that x equal to xi summation over j over all index whatever value are taken by j, and I have to add this joint probability mass function. So joint probability mass function of x from joint probability mass function is given by this. Probability that x equal to xi is summation over all j values of this joint probability mass function. So like this. Similarly, if someone want to calculate marginal probability mass function of y, so it is probability that y equal to yj and p dot j. It means I is running to over all range of x and j is fixed. So I goes to 1 to infinity, probability that x equal to xi and y equal to yj. So this will give me the marginal probability mass function of y from the joint probability mass function of x and y. So we come back to the question again. So in that question, we have to find the marginal probability function of x and y. So first we calculate marginal probability mass function of x. So that means I want to know what is probability I dot. So it means j is varying. So and I know that in that problem j is taking these two values 1 and 3. So summation j comma 1 3 pij, that is summation j13 probability that x equal to xi and y equal to yj. In that particular case, xi is I and yj is j. So it means for j13 probability 0j and it is 0103. So if you see 0103 is this one. So if I add these values of this row, I will get 1 by 8, and this summation of row values will give me the marginal probability mass function at the point x equal to 0. Similarly, to get the marginal probability mass function for x equal to 1, I add these two values.
That's why the X-ray reflectivity
Y is 0.
went out. And this X-ray reflectivity basically
Okay, it is not written here. I thought
and the density of the
maybe
so
here.
the particular case
We
of
write
X-ray
it again.
reflectivity
Okay, he has not written here. Okay. So what I have to do actually, I have to add this. So I have to here write one column, and in that I will write probability x x equal to xi. I have to write, and then I have to add, like in this first line I am having 1 by 8, second I am having 0, third I am having 0, and fourth I am having 1 by 8. So like this we have to do. So, so like we add P0 and P03, we get 0 plus 1 by 8, we are getting 1 by 8. For I equal to 1, it is Pi dot, and we have to add over all j values. So P1j, and j is taking 1 3, so P11, P13, so 3 by 8 plus 0, we are getting 3 by 8. And P2 dot, it means summation J13, P2J, 3 by 8 plus 0, you get 3 by 8 and then 1 by 8. So you have calculated here marginal probability mass function of x. So for x equal to 0, it's having value 1 by 8. For x equal to 1, it is having 3 by 8. For small x equal to 2, it is having 3 by 8. For small x equal to 3, it is 1 by 8. Similarly, we can calculate for y also. So p dot j, summation 0 goes to 1 to 3, because here we have I is taking value in a sequence 0, 1, 2, 3. Pij, it means for j equal to 1. So p dot 1. So I have to add over all values of I, p01, p11, p21, and 31. So after adding, I will get 6 by 8. And you can see that it's a column sum of the values of y here. If I add these values present in the column, I will get the probability mass function of y at this one. I will get probability y equal to 1 after adding, and that will be this 6 by 8. Similarly, if I add this, I will get a probability at y equal to 3, and that is 2 by 8. So like this, and that. So this is the joint, so the marginal probability mass function of the, we have calculated for y from this joint probability mass function.
Sir,
Hmm.
sir, we have test from 2 p.m. Sir, question is almost arrived.
Okay, then you all leave now. I will give present today to all
Okay,
of you. Okay.
So there is a vertical computation and a horizontal computation and a horizontal computation, vertical computation. Different approach to design expression. So it's a you basically we are going to you get the lambda, this is 0.8. So this is basically gives the idea about how much